All right, now we're going to look at section 5.2. And 5.2 introduces a really kind of cool type of arrangement called a matrix. A matrix is a regular array of numbers enclosed in brackets. And in this particular case, we could represent that 3 equations and 3 unknown kind of problem that we were solving before, but now we've got it done as a matrix. So here are the coefficients that were in front of the x, y's, and z's, and then here were our answers to each equation. The line here is really just to separate these two pieces. Columns are considered up and down, rows are considered left to right. And again, the vertical line, which is optional, separates the coefficients from the constants. This matrix has 3 rows and 4 columns. Its dimension would be 3 by 4. Please note, whenever you see that kind of thing, the number of rows goes first, and then the number of columns. But this is going to offer us a way, first of all, of solving systems of equations. And really, you probably noticed in the last section the amount of work when we went from solving 2 equations and 2 unknowns to 3 equations and 3 unknowns was quite a bit more. Well, this allows us a way to go to any set. We could go to 4 by 4s and 5 by 5s. In physics, very often they will do 4 by 4s in which the 4th variable is time. And so this gives us another way of solving these things without really quadrupling the amount of math involved. Now, there are some things that are true about matrices. That's the plural for matrix. Any of the following transformations will result in a matrix that is equivalent set. So that means doesn't really change the overall value of the system. You can interchange any 2 rows. As I said before, it really doesn't matter which one you label which. So if we said this was number 1 and that was number 2, it doesn't change anything. You can multiply or divide the elements of any row by a number, a non-real zero number. This is always true for any equation. So for instance, if I doubled everybody in this one, it would still be a true statement. If x plus y plus z equals 6, then 2x plus 2y plus 2z would have to equal 12. And we can replace any row of the matrix by the sum of the elements of that row and a multiple of the elements of another row. That's kind of complicated sounding, but basically that was the same thing we were doing in the last section when we would say, hey, let's double everybody, say in row 2 here, and then add it to row 3 to get rid of the y's, for example. It's that same kind of thing. So these transformations are true about any matrix. Now, what we're also going to focus on in this section is what's called the Gauss-Jordan Method to solve a system of equations. We'll first look at doing 2 by 2s, and then we'll look at some 3 by 3s. But first off, the idea is you want to attain a 1 as the first element of the first column. So basically that position right there, you want that to be a 1. There are various ways you can do that, but that's the idea. You want to get a 1. Then you want to use the first row to transform the remaining entries into zeros. So notice how these are zeros. Okay, then you want a 1 as the second entry in the second column. So you want a 1 there. And then you want to get the other ones in that row to be zeros. And then finally you want to keep doing that. So if we had only had a 2 by 2, then we would want to be something that would look like that. 1 0 across that diagonal and 0 0 across the other. If it is a 3 by 3, then we want to end up with a situation that looks like that, in which we have 1 1 1 across the diagonal and the other 6 were all zeros. And of course you could repeat this for as many rows and columns as you have. What you want, though, is the end result is it to look like this. And then over here, these will be whatever was the result of all your different transformations, but that will result in x is A, y is B, and z is C, and you will have solved this system of equations. And while it might look a little complicated at first, it really is a somewhat simpler way of dealing with all of those eliminations and substitution methods that we were doing in the previous section. So that's the idea. Now, the Gauss-Jordan method proceeds column by column from left to right if the number of rows with non-zero elements to the left of the vertical line is equal to the number of variables in the system, then the system has a single solution. However, if you end up with a row in which they're all zeros and an A, and as long as that A is not zero, then you will have no solution for your answer. And so just like what we were doing before, you can end up with a no solution. So let's go ahead and solve some of these problems and see how working with matrices works. So first off, we're going to rewrite our two equations and two unknowns in matrix form. So 2, -3, -3, 1, draw my line, -6, -5, and then the closing bracket. So again, notice how these numbers here came from the coefficients, and these numbers here came from that. All right, so I want to get a 1 right there. And of course, there's a number of ways to do this. For instance, I could just cut everybody in half. I like to try to come up with arrangements that don't give me fractions before I have to have them. And so in this particular case, what I'm going to do is I'm going to do -1 times row 1 plus a -1 times row 2, and then put that in row 1. So the 2 will become a -2. The 3 will become a +3, 3, and then add, so 3 minus 2, that'll give me a 1 right there, and change that one. So let's go ahead and look at that. So again, the 2 will become -2, the -3 will become +3, add them, I will get a 1. Here, that'll become a +3, that'll become a -1, so when I add them, I'll get a 2. Here, that'll become a +6. That will become a +5. Add them together, I will get an 11. Now, in this case, that is how I have changed row 1. I didn't do anything to row 2, so it is still -3, 1, and -5. But I have transformed that first one and gotten a 1 there. Okay, so now I'm going to get a 0 right here, and I'm basically going to do that by going 3 times row 1 plus row 2 and put it in row 2. So what I'll do is 3 times 1 will be 3, 3 plus a -3, that'll give me a 0 there. So again, I'm not going to be changing row 1 at this point. So 3 minus 3, that gives me a 0. 3 times the 2, that's 6. 6 plus 1, that's 7. 3 times the 11 is 33. 33 minus the 5 will be 28. And so now I have that. Okay, and the idea is that, see, now that I have that 0 there, no matter how I take row 2 at this point and add it back to row 1, because I want to get a 0 right up there as well, that's a 0, so nothing I do will change that 1. It'll stay a 1 from now on. So now we're going to take row 2, and we're going to divide by 7, and that'll give me a 1 right there, because remember, we want 1s along the diagonal. So all I'm doing is changing row 2, so row 1 doesn't change. And so divide by 7, 0, 1, and 4 is what I have now. And now the last part is I want to get a 0 up there, so I'm going to take negative 2 times row 2 plus row 1, and then put that in row 1. So, and again, I'm not changing row 2 in this case, I'm only changing row 1. Whatever I say put it into, that's the row I'm changing. And so negative 2 times 0, well, that's not going to be anything, that's still a 1 up there. Negative 2 times the 1 is negative 2, negative 2 plus 2, that's a 0. Over here, negative 2 times the 4 is negative 8, negative 8 plus 11 gives me 3. So, now I have the form I want. X equals 3, y equals 4, and my answer is 3, 4. Now, in a 2 by 2 case, you could certainly make the argument, is this really any simpler than what we were doing before? This is the same problem that we did in section 1. But what you'll see is, the power of this is we got to bigger and bigger systems. In other words, 3 by 3s, 4 by 4s, or so forth. This does become an easier process. It may not be over in short order, but it does become an easier process to solve more complicated situations. So let's go ahead and look at problem 2 now. Again, let's rewrite it in the matrix form. 3, 2, minus 5, minus 3, negative 2, 1. Again, I want a 1 up here, so this time I'm going to do a negative 1 times row 2 plus row 1, and then put that in row 1. Do you have to do all this labeling? I think it really helps if, in the end you've made a mistake and you want to go back and make sure that what you thought you were doing is actually what you did. But I would recommend always putting these kind of little notes to yourself. So 2 becomes negative 2, and 3 gives me a 1. That becomes a positive 3. 3 and negative 5 becomes a negative 2. Negative 1 and negative 2, that's a negative 3. And then, of course, we did not change row 2. So again, we did that. We got that to be a 1, and now we want that one to be a 0. Okay, so in this case, I'm going to take negative 2 times row 1 plus row 2, and I'm going to put that in row 2 so that I can make that into a 0. So I'm not changing row 1 at all. So negative 2 times 1 is negative 2. Negative 2 plus 2, 0. Negative 2 times negative 2 is 4. 4 minus 3 would be 1. And negative 2 times negative 3 is 6. 6 and 1 is 7. Now in this particular case, that also got me a 1 right here, which would have been my next step to make that into a 1, but it's already 1. So now all I have to do is turn that into a 0. So I'm going to take 2 times row 2, add it to row 1, and put that in row 1. So row 2 isn't changing. And in row 1, 2 times 0 plus 1 is 1. 2 times 1 is 2 plus a negative 2 is 0. 2 times 7 is 14. 14 minus 3 is 11. And so I've left with x equals 11, y equals 7, and my answer is 11, 7. So these were the same problems that we had in section 1, but now we have solved them using the Gauss-Jordan method with a matrix. All right, so let's go ahead and do this now with the next one. 3 by 3, 3 equations, x, y, and z, 3 variables. So we have 2, 2, negative 2, negative 4, 4, 2, 1, negative 6, 4, 1, 2, 2. So I want a 1 there. And so I'm going to take, again, I could just say, hey, divide everybody here by 2, but that would give me halves for these two parts. I try to avoid that. However, I notice that everything in row 2 is an even number, so I'm going to take half times row 3, add it to row 1, and put that in row 1. So half of negative 2 is negative 1. Negative 1 plus 2 gives me 1. Half of 2 is 1. 1 and a negative 4 gives me a negative 3. Half of 4 is 2. 2 and 1 gives me a 3. Half of 2 is 1. 1 and 1 gives me a 2. And then I did not change the other 2. Okay, now I'm going to do negative 2 times row 1 plus row 2 and put that in row 2 because I want to get that 0. So I'm not changing row 1 at all. But negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times that is 6. 6 and 4, 10. Negative 2 times that is negative 6. Negative 6, that's negative 12. Negative 2, that's negative 4. Negative 4 and 2, negative 2. Did not change row 3 at this point. Okay, now I'm going to do a similar thing. Negative 2 times row 1 plus row 3 and put that in row 3. So I'm not changing row 1, not changing row 2, changing row 3. So again, looking at this one, negative 2 times the, let's see, yeah, let's see, negative 2 times row 1 plus row 3, Actually, I just want a positive 2. I don't want a negative 2. I just want a positive 2. Positive 2 times 1, so 2, negative 2, that gives me a 0. And then I have 2 times negative 6, and 2 gives me negative 4. And then 2 times 3, that's 6. 6 and the 4, that gives me 10. 2 times the 2 is 4. 4 and the 2, that gives me 6. So this was a positive 2 in this case. All right. Let's see. The next thing I want to do is I want to end up with a 1 right there. And so one way I can get there is I'm going to take half times row 2, add it to row 3, and put that in row 2. Now I know that's a little bit complicated, but half of 10 will be 5, and then 5 added to the negative 4 will give me a 1 there. That's what I'm looking for. So, not changing the top row in this case, and I'm not changing the bottom row at this point, just changing the middle row. Of course, 0's not going to do anything to 0. So, as I said, half of 10 is 5. 5 minus 4 gives me a 1. Half of 12 is negative 6. Negative 6 and 10 gives me a 4. Half of negative 2 is negative 1. Negative 1 and a 6 is a 5. And so now I have that 1 there. And so now what we want to do is make the negative 3 and the negative 4 both zeros. So first off, I'm going to take 3 times row 2 plus row 1 and put that in row 1. And so it's not going to change row 2 or row 3. Of course, 0 and 1 is just 1. And here, 3 times 1 is 3. 3 and a negative 3 gives me a 0. Here, 3 times 4 is 12. 12 and 3, that's 15. 3 times 5 is 15. 15 and 2, that's 17. But I do have my 0 there now. And then I'm going to take 4 times row 2 plus row 3, and I'm going to put that in row 3. And so since I'm changing row 3, row 1 doesn't change, and row 2 doesn't change. So 0 and 0, that's still going to be 0. 4 times 1 is 4, and a negative 4, that's 0. 4 times 4 is 16. 16 and 10 is 26. 4 times 5 is 20. 20 and 6 is 26. So note, over here I made that first one a 1, and then I went after the other ones to make them zeros. Then I made this one a 1, but then I could go after the other two in that column to make them zeros. And so now I'll make that next one a 1. I'm going to take row 3 and simply divide by 26 because I have 26 and 26 here. Sorry about that. So again, since these are both 26, I can just divide them both by 26 and I'll get a 1 there. So I have 1, 0, 15, 17. I have 0, 1, 4, 5, not changing rows 1 and 2. And now I have 0, 0, 1, 1. And so 2 more steps to go. I'm going to take negative 4 times row 3 plus row 2 and put that in row 2. So again, this one didn't change at this point. And so 0, 1, 0, 0, 1, 1. And so negative 4 plus 4, that's a 0. Negative 4 plus 5, that's a 1. And now I'm going to take negative 15 times row 3 plus row 1. Put that in row 1. And of course, this is not going to change row 2, not going to change row 3. 0 and 1 is 1. 0 and 0 is, of course, 0. Negative 15 times 1 plus 15, there's my 0. Negative 15 times 1, negative 15 and 17, there's my 2. And so I'm left with x is 2, y is 1, z is 1. And my answer 2, 1, 1. Now, is this really less work than what we did in the last section, solving 3 equations and 3 unknowns? I'm not sure it looks like less work. I think part of it is that I'm just doing the same kind of process over and over. Make this a 1, turn the other ones into zeros. Make this next one a 1, turn the other ones into zeros. And so there's a little bit of trying to figure things out in that sense. But in the other case, I'm always, all right, which letter am I going to pick? I got to make a match so that one's positive 3, one's negative 3, that kind of thing, so that they can cancel out. And then I got 2 equations and 2 unknowns, and now I got to do that again. And then I got to go plug them all back in to find out the missing variables. So, a little bit, half a dozen of one, 6 of the other kind of idea. However, maybe you could see here it's just the same kind of steps over and over again, even if it's a little bit tedious. And then, like I said, this I can now go to a 4x4, do exact same kind of process, or a 5x5, and so forth. So it really does give me a methodology for solving this, no matter how many equations and how many unknowns I might have using the Gauss-Jordan method. Okay, now let's look at our last example. And first, if we write it, 1, negative 5, 4, 8, and then we have 3, 1, negative 2, 7, negative 9, negative 3, 6, and 5. Now, if, I notice something, hey, if I take 3 times row 2, and then add it to row 3, and put that in row 3, I'll have this result. So I'm not changing 1 at all. Not changing 2. But now row 3, 3 times 3 is 9, 9 and negative 9, that's a 0. 3 times 1 is 3, 3 and negative 3, that's a 0. 3 times negative 2, negative 2 and negative 6 and 6, that's a 0. 3 times 7 is 21, and 5, that's 26. And note, in that third equation now, I have 0 equals 26, which of course is not true, and therefore there is no solution. And it just goes to show that, I already had a 1 here. I wanted to end up with a 0 there anyway, and it really didn't matter whether I worked on row 2 or I worked on row 3. I needed both these guys to be zeros, but in doing row 3 here, I ended up with a situation that I know can't be true. 0 does not equal 26. Or in terms of equations, 0x plus 0y plus 0z equals 26. That can't be true unless all x, y, and z's were all zeros, of course. And so I've gotten a no solution for these. I might also mention, before here, once I had that 1 down there, I worked upwards, but I could have gone right to row 1 and then back down to row 2. The rows are independent of each other. We just like to get those 1s first because then it allows us an easy multiplier to get rid of either the first column, the second column, or third column. But these were all the same examples that we had in section 1, but now we have solved them using the Gauss-Jordan method and introduced the idea of matrices. And as we go along in the chapter, we'll learn more things that we can do with matrices and some of the things that they allow us to do that we would not have been able to do very easily any other way. So, section 5.2.